Okay. What is the shortest distance between 2 points? We hear this a lot. The shortest distance between 2 points is a straight line. It's not going to be across and then up some distance. It's not going to be in a weird circle distance. Assuming there are no obstacles or constraints, the shortest distance between 2 points is always going to be a straight line. Now, there's a lot of ways to colloquially say this, but how do we say this mathematically? Well, one of the ways we can say it numerically is by the triangle inequality theorem, which says that if I have any two numbers, real numbers, that if I take their sum and then take the absolute value of that sum, it is less than or equal to the absolute value of each of those two numbers being added together separately. In other words, if I traveled an absolute value distance of A, and then I traveled another absolute value distance of B, that's always going to be less than the distance between the 2 points had I traveled in just a straight line. And this is the numerical way of saying that. Now, we're going to prove this, but one of the first things that we need to understand is how we are going to define what absolute value means. Now, the absolute value definition is written in this way, where we write with these bars here, and it's written with these constraints, where it's positive if it's greater than or equal to 0, so the sign is positive. If it's negative, less than 0, then we multiply by a negative sign to flip the sign back. And then there's a corollary that follows from this, that for any real number, the absolute value of that real number is going to be less than or equal to another real number, if and only if it's between the negative of the second number and the positive of that same number. So then we're going to prove this little mini theorem that for an x being a real number, it's going to be between the absolute value, or minus the absolute value of x, and the positive absolute value of x. So first off, we're going to note that if I took the absolute value of the absolute value of x, it's going to be a real number because x was a real number in the first place. So the absolute value of x is going to be a real number, and the absolute value of the absolute value of x is going to be a real number. And then we're going to quote the absolute value definition. It's going to be nested with these absolute values. And we also know that the absolute value of the absolute value of x is going to be greater than 0, because by the definition, the absolute value of x is also going to be greater than 0. So then the absolute value of x is going to be less than or equal to the absolute value of the absolute value of x, if and only if the absolute value of x is equal to the absolute value of the absolute value of x. And this is true because there are two cases here. Either the absolute value of x is going to be less than or equal to the absolute value of the absolute value of x, or it's going to be greater than or equal to the absolute value of the absolute value of x. And since these are by definition equal because they're both positive, this is going to be the same as that. And so we actually only have one case. And so by definition of our corollary over here, we can say that x is going to be between the negative absolute value of x and the positive absolute value of x. The second way we can word this is we can quote the definition again, and then we can graph these domains. So if x is positive, it's going to go all the way up to the positive of the absolute value of x. If it's a negative, it's going to go all the way up to the negative of the absolute value of x. This means that x is going to be up to 0 here, and then it's going to be less than or equal to absolute value of x. And for over here, x is going to be the lowest value, 0. And it's going to go all the way up to the positive absolute value of x. And so if we merge these two inequalities together, we're going to get this inequality, which is what we had earlier. So that's our little mini proof for what we're going to call theorem 1. Now we're going to prove the triangle inequality theorem. First off, we're going to let a be a real number. That's going to be our first number in our number pair. Then, by the theorem 1 corollary, a is going to be between negative absolute value of a and positive absolute value of a, and likewise for b. Now, if we add these two inequalities together, we're going to get this bigger inequality, which, if we reverse and flip the absolute value definition, we're going to get this inequality, which is actually the triangle inequality. Now, we're going to do a second theorem, something else that we need to understand. What happens if we flipped the order of two numbers being in here? We need to show that whenever we flip it, it's going to be the same value when we take the absolute value. This is just to say if I had 2 points, x and y, that their arbitrary distance is always going to be positive, even if I subtracted it in opposite order. So we're going to let x and y be real numbers, where x is not y. And so by the absolute value definition, we're going to look at y minus x, and y minus x is going to be positive if y minus x is greater than or equal to 0. And we're going to multiply by that negative sign if y minus x is less than 0. And likewise for x minus y is going to be greater than 0 if it's greater than 0. And if it's less than 0, we're just going to multiply by that negative sign to alternate it and switch it back to positive. Now, here's a cool thing that we can note. If we took x minus y is greater than or equal to 0, which is this constraint here, and we multiplied by a negative, we'd be effectively entering the domain of this guy. We'd be flipping the sign, which we'd be getting into y minus x is less than 0. And likewise for x minus y being less than 0, if we flip the sign by multiplying by -1, then we get y minus x is greater than 0. And likewise, if we graph this, we can show that we can jump between these two domains. And the algebraic proof is as such. If we had y minus x, or consider y minus x, the absolute value of y minus x, it's equal to minus x minus y, distributive. I factored out a -1. And so now we know that x minus y, this little operating expression here, that's going to be less than 0 because it's negative. And so, if it's a negative, we can multiply by a negative by the absolute value definition, and we can drop the absolute value bars, and that shows us that this is y minus x, which is the absolute value of y minus x. So we can swap it and we can swap it back. So now let's talk about another weird corollary. It's called the reverse triangle inequality theorem, which basically says that if for any two numbers x and y, if I took the absolute value of x minus the absolute value of y, and that's going to be less than or equal to the absolute value of x minus y. And notice here, it really is the flipped version of the triangle inequality theorem, because if we took the regular triangle inequality theorem, we had a plus here. Over here, we're using minuses. And also notice that this two merged part is on the right-hand side, whereas in the regular triangle inequality theorem, it's on the left side. So it really is the reverse triangle inequality theorem. So this is going to be a little bit unique because we're going to prove the right-hand side first. That is, we're going to show this part. And then in the next part of the proof, we're going to show the left-hand side, this part. So we're going to make a substitution. We're going to let A equal x minus y, and we're going to let B just equal y. So by the triangle inequality theorem that we just proved earlier, if we add these two numbers together, we have this. This is literally the triangle inequality, theorem. Then we can substitute in our values for each piece. Then we can drop the parentheses, and we can see that this y and this y cancel. And we can move this y over to the other side, which gives us a minus y over here. And now we see that the absolute value of x minus y is less than or equal to x minus y. Let me correct that really quickly. That should not be. Let me double check that. Yes, that's correct. Okay. Now let's prove the left side. So for the left side, we want to show that minus x minus y is less than or equal to minus x, absolute value of x minus the absolute value of y. So now we want to let that c equals y minus x and d equals x. So by the triangle inequality theorem, we see that c plus d, the absolute value of c plus d, is less than or equal to the absolute value of c plus the absolute value of d. We plug in our values again, our substitutions. We make the cancellation again. We move x to the other side. And now we see that this is the absolute value of y minus the absolute value of x. It's less than or equal to the absolute value of y minus x. And we can make this jump right here by theorem 2, which, if you don't remember, that was if we wanted to swap it. So over here, it was y minus x, and we swapped it to get x minus y. And we multiplied by a -1 to get rid of this minus sign here. And now we have the absolute value of x minus the absolute value of y is less than or equal to minus the absolute value of x minus y. So that's the left-hand side. And from this, we can say by the absolute value definition, I can scroll up here. The absolute value of x, or the absolute value of the absolute value of x minus the absolute value of y is less than or equal to the absolute value of x minus y. So that's the regular triangle inequality theorem, the reverse triangle inequality theorem. Now let's take a look at the geometric triangle inequality theorem. So, if we have a triangle, let's call it ABC. It's this orange triangle here. What we want to say is that side, or the length of side BC, written with these bars here, this length is going to be less than or equal, or is going to be less than the length of AB right here plus the length of AC right here. And that's what we're trying to prove. So we're going to consider triangle ABC, which is what we just talked about, this little orange triangle here. And we're going to take a side, so we picked side AB, and we're going to build an isosceles triangle by connecting this green triangle here across. And we're going to pick a point D to connect the third point. It's going to be reflected across this leg AB, this side AB. So it's going to share one of its congruent lines with the chosen side of triangle ABC. In this case, it chose line AB. So this should have a third point D, which we labeled D, and share 2 points from ABC. In this case, triangle ABD shares points A and B. So we're going to call this isosceles triangle DBC, or sorry, yeah. So we're going to call the bigger triangle isosceles triangle DBC. Let me draw this. That would be this triangle here. That's DBC. Where DBC shares points BC from ABC. So from the law of sines, which we won't prove here, the length of BC and the ratio of the sine of angle A right here and the length of BC right here is equal to the ratio of angle B here and the side length DC right here, this big one right here. That's DC. And to clarify, these bars here is the length of BC, and the bars of DC is going to be the length of side DC. Since angle A is congruent to a component angle of angle B, right here, A is going to be less than B. So the length of side BC is going to be less than the length of side DC. So, or also, the length of side DC is going to be equal to the length of side AB plus the length of side AC. And we can see that with the triangle here. DC, if we chopped it up into pieces, is AD plus AC, or DA plus AC, whichever one you want to call it. So then side length BC is going to be less than side length AB plus side length AC. And that is the last proof of this video. Thank you for watching.